The idea of the improper integrals is, basically we were lying to you for a while that all integrals are proper, but actually they're not. Some integrals are just not made as a definition of the integral. Let's see what I mean. Let's try to integrate from 1 to 2, 1 over x squared dx. That is something pretty straightforward. We had it before. How would you integrate that? X to the minus 2, so minus 2 plus 1 minus 1. The answer will be minus 1 over x. I'm skipping explaining that. I think you're already good at integrating. Plug 2, plug 1. You'll have minus 1/2 minus plug 1. So it's going to be plus, well, minus 1, which is 1/2. Done. Everything is nice. That's what we were teaching you. Everything is fine. That is a proper integral. So let's make it right. It's not improper. It's not improper integral. So let me show you what's the difference. B. What if we want to integrate from the same function 1 over x squared dx from from 1 to infinity. Boom, this is something we never seen before. From 1 to infinity. And we're going to have from minus infinity to 1, and we're going to have from minus infinity to infinity. This is what they call improper integrals type 1. We will have several types. Type 1, infinity at the top, minus infinity at the bottom, and infinity at both sides. Let's see. So if the limit exists when the improper integral converges, and if the limit doesn't exist, then the improper integral diverges. This is the first time we introduced notation and terminology as divergence and convergence, and we're gonna use it quite a lot later. Equals. So what is happening is, let me show you on the computer. What is happening here is this. This is actually pretty good notation here. You don't have to, you can draw it if you want, but it's actually really good. It is 1 over x squared, like so, exactly like on the graph, f of x. Then we're fixing it at a, in this case 1, and then we're doing like so. Area starts at 1, and then it doesn't end. Like there is no ending point to it. They told us to go to infinity, so it goes to infinity. So what's gonna happen? Intuitively speaking, you will say that the answer is probably infinity. But the answer is not necessary. Somehow adding infinitely many things not necessarily gives you infinity. Check it out. We're adding those heights, right? And then at the very end, we add those heights infinitely many. So maybe you think it is infinity, but maybe it's not. And that will be very interesting to explain to people how come infinitely many little pieces add up together gives you a finite answer like 3/2 or pi over 2. So this is a nice animation that shows you again how it accumulates. Improper integral accumulates. And you can go to minus infinity, plus infinity, and that's why it's also using parameter t. You can go as far as you want or as close as you want. So this specific example sometimes has a name in applications of mathematics and biology or engineering in the long run. What is happening in my fish tank in the long run if this function represents how my fish is reproducing in my fish tank, right? So at some point the population of the fish decreasing, so will be the finite number or not. In the long run is when you look at t goes to infinity. So in 2 years, in 5 years, in million years, technically speaking, human beings cannot calculate or look at the million years, but math can. And that's why math is so amazing. Humans using math to go into the future and into the past, using limits. That's what takes us to the subject of limits, back to your favorite topic. If you cannot touch something, but you really want to get there, that's called limiting position. And that's why it was so super important but extremely annoying topic at the very beginning of Calculus 1, is to learn limits. If you cannot approach 5, but you get into number 5, but you really want to get super close to it, limit will do it for you. So let's create a limit. Let's use a third variable, for example, t, and then let t go to infinity for u. Then the integral will be from 1 to t. Boom. Now it's a definite integral. You know how to figure out definite integral until you hit the limit situation. So 1 over x squared dx. We will first calculate this part as a typical definite integral, which we learned. And then we're going to calculate limits. So this chapter merges together two topics, integration and limits. Again, the idea is if you cannot reach infinity, at least try to approach it. And that's what limit does for you. So let's do it. So we're introducing the upper bound and call it t, and tell t to go to plus infinity. That's what we're doing here. Now, we're going to ditch limit for a while, but we will keep writing it to remember that this was improper integral. We're going to integrate from 1 to t 1 over x squared, which gives us minus 1 over x bar from 1 to t. We're still integrating. We don't touch limit first. Limit is just there reminding us that t actually is a moving variable. T is moving to plus infinity. For now, we're treating it as just a normal number, some kind of number. Equals limit t goes to infinity, plug top minus the bottom. You will have minus 1 over t minus negative 1. And this is the moment of truth. If now, when limit comes into the picture, the answer blows up to infinity or minus infinity, then the integral is called divergent. It blows up. If we have a final answer right now as a number, then it's convergent. So it converges. It's a stable integral. That's also the idea of some kind of chemical reaction blowing up or being stable. So I like to involve explosions in my teaching a lot, and students made lots of memes about it. It's somehow like I really like explosion, and I will explain you in this chapter how do we know what's going to happen if you put an explosion of the creation of the nova star when it shrinks so much into itself that it explodes into a black hole that actually sucks everything in. Who is going to win? It's going to be a huge explosion, or it's going to be shrink to nothingness. So we're going to do this in this chapter. That's what I like about those examples of explosion, that they're just awesome. And then it's kind of fun to see that. But it's all math, so mathematics can give you the answer for those questions. That's why it's so cool. So now it takes you to the chapter of limits. Let me simplify to make it look easier. Minus 1 over t plus 1. This is calculus 1. We take you back to calculus 1, chapter 1, limits. You plug t, well, not you don't plug t. You send t to go to infinity. Now this is the moment you actually tell yourself, oh, t is actually going to infinity, right? So how do you solve limits? Let me remind you. If t is going to infinity in the denominator, then this whole thing goes where? To 0. Remember, I actually can review it here. This is how I teach in my classes. If there's a number a over infinity, that's limits. It's not just a divided by infinity. That means there's a over b, but b goes to infinity. Exactly what we have here. 1 over t, but t goes to infinity. Dividing by the biggest numbers you know gives you the smallest number you know, which is 0. And you can always check. Plug t equals 1 million. 1 over 1 million is a really, really small number. So it's almost 0. So if the first term is minus 0 plus 1, the answer will be minus 0 plus 1, which is 1. Since we have a finite number, we're going to say that the answer is, so this goes to 0, the answer is, the integral from 1 to infinity of 1 over x squared converges integral converges, and not just converges, we even know to what? To 1. That means that the area here, even though it is infinitely keep adding more and more pieces, the area below this graph, 1 over x squared, starting from 1, was accumulating, and it will be keep accumulating more and more and more, just gets tinier and tinier and tinier, but the total number is found. No matter how much it keep adding, something at the very end will be so tiny that it will not make a difference anymore. So the total number is 1. 1 unit, 1 meter, 1 whatever, kilometer, why is the same distance? Okay, 1 pounds, and so on. Does that make sense? So it's very interesting and new to imagine for a human being that something infinitely accumulating converges to 1. That's a pretty cool idea. That's a new idea for us. So let's write down the definition. Definition. DEF, definition. If the result of improper integral is a finite number. Let me know if you don't like my handwriting. I can fix it a little bit or read it for you. Then integral converges. Integral converges, and it converges to that number. Converges. And it's called convergent integral. If it's not a finite number, guess what? It diverges, and it's called divergent integral. Otherwise, its integral diverges, and it's called divergent integral. So all of this ends up to be of the question of the limit. Does this limit exist or not? And that's the end. That's what our job or your job is to figure out when you calculate limits at the very end. So we learned that this particular integral converges, and the pretty cool idea is we knew before from calculus 1 that y equals 0, which is this floor, or basically x-axis. In this case, it's t-axis. This is horizontal asymptote. So the graph of the functions keeps shrinking to horizontal asymptote. The areas keep accumulating forever, but at the very end, they are so tiny that the whole accumulation at the tail does not make a big difference anymore. So the whole area converges to 1. Does it always like that? No. So let me show you a famous example of integral of 1 over x. Integral of 1 over x dx. And it's going to be the same from 1 to infinity. Example 2. 1 over x brings lots of troubles into calculations in engineering and physics calculations. It kind of shows up everywhere. And it's problematic mostly actually because integral of 1 over x is log, and logarithmic and 1 over x functions have lots of restrictions. Log does not exist for negatives and 0. 1 over x has denominator, and so on. So in general, 1 over x actually sometimes shows some kind of bad behavior. So people would like to avoid it. We'll see what is the difference. We're going to remember this new notation we just learned. Notation is, if you cannot reach something, introduce limit. Limit will do it for you. Let me change notation a little bit for you. People don't necessarily use t or, well, I just showed you t. Sometimes people just call it b because it's from a to b, right? So it's from 1 to b. b goes to infinity. Doesn't matter. This letter you're using is just intermediate calculation letter. It disappears at the end. So just like u substitution can be called m substitution or t substitution, it's a dummy variable. Nobody cares how you call it. You can use this first letter of your name. So we're dealing with the integral first. We keep writing limits, but we don't use them yet. Integral of 1 over x is what? Natural logarithm, absolute value of x, exactly. From 1 to b equals limit as b goes to infinity. We don't do that yet. We're first still integrating. So some people put brackets or parentheses, but actually you don't have to. You will have ln, absolute value of b, minus ln of 1. As you can see, absolute value is not necessary for both cases. Absolute value of 1 is 1, and b is not negative because it starts from 1. b goes from 1 to infinity. So to be honest, that is not necessary. But it is not a mistake if you keep it. It's just a bit an overkill. Now, what is ln of 1? 0. So limit b goes to infinity. ln of b, well, let's drop absolute values. ln of b minus 0. This is what we're dealing with. Let me write it down that this is 0. Now everything is happening with the limit. Limit will decide will this integral survives and then becomes a finite number, or it blows up as an explosion. But what does logarithmic function do at infinity? Wow, people remember? No, you guys don't remember. Let me tell you, there are two ways to do it. Either you plug big numbers and see. If you plug in your calculator ln of a million, what it's going to do? Will it shrink to 0? Gives you d and e. Maybe it doesn't exist there. Is it going to be big numbers? You can check. But we kind of hope you remember the graph of it. And the graph of logarithmic function looks like so. It's actually inverse of e to the x. And the inverse is created by using this y equals x line as a mirror. So y equals e to the x, y equals ln x. Well, it's actually log. This is how it looks like. Inverse functions. So logarithmic functions, even though it looks pretty sad, it actually keep growing. By sad, I mean concave down. It's actually keep growing forever. It doesn't have an asymptote, but it just grows slowly. So it goes to infinity, but slowly. Moreover, usually I raise my finger. Moreover, logarithmic function is the slowest function goes to infinity. And that's why it's used in many applicational sciences as axis for calculations. Sometimes you will attend a conference or a talk where people show some data and they say, pay attention, my axes are in terms of log. So it will be not x and y, it will be log x and log y, because logarithmic function slows down the process. If you're working with chemical reactions and then you make something up and it explodes, the graph will look like this. And that doesn't give you any information, so that is bad. You need to learn how to mathematically zoom it in or slow it down. So if you slow it down, you can see how it actually was bumping up. So people apply log to both axes, and then it becomes like so. The chemicals were added, it was some kind of bifurcation happening, and then grows up. So that's why usually they present it, and they tell people at the conference or presentation, pay attention, I use logarithmic function to slow down the process and show you what is happening. And then you can always undo it. If you apply e to both sides, it goes back to the original graph. So logarithmic functions are known to be used everywhere to slow down fast processes and other applications as well. My point is it goes to infinity. That is the most important that we're supposed to remember right now, because we just need to know the final answer for the integral. It is infinity. So integral answer. Integral from 1 to infinity, 1 over x dx diverges. Diverges. We usually don't put equal sign and equals infinity, but that's kind of what you imagine. That it keep increasing forever. And let me show you the graph of this situation. We have the graph of y equals 1 over x. We're starting again from 1, like so. And then just like before, we're introducing an intermediate variable, but this time we call it b, and it goes to plus infinity. So it's keep accumulating, and it keeps shrinking. It keeps shrinking. But unlike before, the whole answer is not the finite number. It gives you not equal sign, because you cannot equal infinity, but it blows up. It diverges. So why? What is the difference? The graph looks almost the same as before. Look at the previous graph. It looks the same thing. So that's very interesting to explain behaviors of the function and what was the difference. In general, the idea is, and that's a pretty cool thing to explain, what is the difference? Let me write it down. The idea is, even though 1 over x and 1 over x squared both shrink to 0 and they both have the asymptote, one of them shrinks to 0 faster. And the faster means fast enough to give you a finite answer. That is pretty cool, that something can shrink to 0 or explode with different speeds. And this is what this chapter is about. We're going to learn what is happening with different speeds of infinities. Is infinity minus infinity 0? Not necessary. One infinity might be bigger infinity than another one, because one universe is expanding faster than another one. Is 0 over 0? Is it 0 or undefined? I don't know which one is which. So we're going to talk about those cool situations. So let me write it down. Even though, let me put it, let's call it note. Even though, I would say even though we're working with integrals and some numbers all the time, and you might be sleepy and think it's all the same math every time, this has lots of phenomenal applications, not only in space science, but automatic cars, which we're building right now, and so on. Even though 1 over x and 1 over x squared they both shrink to 0 as x explodes to infinity or goes to infinity, comma. But 1 over x squared shrinks to 0 fast enough for the integral to converge. Fast enough for the integral, I would say integral later, for the accumulative area to shrink to a finite number, or let's actually write down, for the integral from 1 to infinity, 1 over x squared dx to converge, for something to converge. Is this correct English? I think so. To converge. Let me know if it's not. IA, and this is what we're talking about. We're talking about accumulative areas. We did teach the idea of accumulative area in Calculus 1 at the very end of the class. Accumulative area, when area accumulates. It's not a new topic or anything. It comes from this title. For the accumulative area to converge to 1, a finite number. A finite number. And this is something new, which is pretty awesome, that infinite stuff converges to a finite number. If it shrinks to the horizontal asymptote fast enough, horizontal asymptote is here. Basically, the idea is, if the function hugs the horizontal or vertical asymptote, soon then the total area will be finite. If it's too slow to hug it, then it's keep accumulating so much area that now it explodes to infinity. That's what it means for a speed to be faster or slower. 1 over x also hugs or approaches HA, horizontal asymptote 0, but it's too slow to do it. So apparently, if you put a power, it converges. If you put a power 5, it converges. If you put a power 100, it converges even faster, and so on. And converges to different numbers. But 1 over x is just slow. So, bless you, all this comes to the theorem about p integrals. Theorem. Those are called p integrals, and soon we're going to go to p series. Integral from 1 to infinity, 1 over x to the p dx apparently converges or diverges depending on p. P is this power. So it converges, and the integral called convergent, if it's convergent. If, and the process called convergence, by the way, that's English. If p is greater than 1, so x squared, x cubed, 1 over x to the 5, 1 over x to the 100 will converge to some number. But then it blows up, which is diverges. Otherwise, if p is less or equal to 1, if it equals to 1, it's 1 over x case, which is log. But then if it's less than 1, it also blows up. Example is integral from 1 to, let's do 2, why not? Doesn't matter if it's from 1 or not. Some number should be avoided, but I will explain it on Wednesday more. If it's dx over square root of x, this integral diverges because BC, p equals 1/2, which is less than 1. And you can check it yourself. Integrate 1 over square root of x, plug 2, and then send b to infinity, and see what's going to happen. It will blow up. Finally, before we leave, I will tell you an interesting story. The terminology I'm using about something to blow up actually is official terminology. We're using it in mathematics and physics when something goes to infinity and blows up. However, there's a very true and funny story of mathematicians going to a conference in America. You will see why it's important that it was in America. They were going to a conference, and they were already waiting for the plane at the waiting zone, and talking about the research they're going to present. And mathematicians get super excited sometimes when you talk about research. So they were pretty loud, and they were showing notes. And then one was saying, I'm telling you, it's going to blow up on the plane. It's going to blow up. He's like, no, I'm telling you, it's not going to blow up on the plane because solutions are off. I'm telling you one more time, it's going to blow up on the plane. Anyway, they got arrested. And that's a true story. It was somewhere in the news. It was a long time ago. It took them 4 hours to prove that they are not terrorists. Because when they were showing their notes and books, it looked like gibberish and all full of math. Finally, they proved they were innocent, missed their flight, and then came to conference late. So that is a nice lesson for you and for me. Don't discuss your research in the airport, especially if you're in America. So for you to know, my research was about Ebola spread in hospitals. So when I would go home to visit my family in Ukraine, I would not take any formulas with me, nothing. And when they would ask me what do, I do differential equations. I was very honest about it. No Ebola, no American hospitals, nothing. You're welcome.